As president of the Swedish Society of Aeronautics and Astronautics, I'm very pleased to welcome you to the 17th Congress of the International Council of the Aeronautical Sciences. Sweden was one of the founders of Icas in 1957, and in 1962 we hosted the third Icas Congress here in Stockholm. We feel very honored to once more be acting as host to the Icas Congress. Like its predecessors, this Congress will provide a great forum for exchange of information about the latest advances in the aeronautical sciences. In the social program of the Congress, we offer some opportunities for you to get together. Tonight there will be a reception at the City Hall where the Nobel banquets take place and where you can practice the noble art of discussion. Tomorrow you have a chance to get seaborne in an evening cruise, and in the program you can find more possibilities. This morning the Stockholm Brass Band has played some happy music for you. I hope that this musical overture will set the tone to this major Congress and that it will be enjoyable for all participants. Finally, I want to express a warm welcome to you, ladies and gentlemen, from the host society in the cool city of Stockholm. I hereby declare the 17th Icas Congress as open. The next speaker will be Dr. Tore Gullstrand from Saab Scania, who has been directing Sweden's major aeronautical projects such as the Viggen and the Gripen aircraft.
Well, good morning, ladies and gentlemen. I will talk a little about aerospace in Sweden. Some people are a little astonished that Sweden, a country of only 8 million inhabitants, has an aerospace industry creating products of high international standard. We cover not only airframes and engines, but also electronics and equipment. My conviction is that even a small organization can take part in advanced programs if there are sufficient planning, political readiness to take risk, and of course skilled industrial leadership. I will try to explain the background of our situation and also our approach to the future. First, a little about our history. The early history of the Swedish aeronautical activities is not much different from that of other small nations. During the First World War, 1914 to 18, we had 2 private industries in the field. The Thulin-verken in Landskrona was quite large, up to 1,000 employees. It designed and built aircraft and engines for the Swedish defense, but also for export. A large part of the 650 rotary engines built on license were exported. After the war, a surplus of aircraft were available on the world market, and the need for new aircraft became close to zero, and therefore the private industry closed down. The government-owned factory at Malmslätt outside Linköping continued on a small scale, mainly for a very small need of the Swedish Air Force. In the 30s, threatening clouds appeared over Europe, and the Swedish government began to fear that war could break out. 1935, the Parliament, or what we call Riksdag, decided to strengthen the defense, and especially the Air Force. And a program for purchase of modern aircraft was launched. These were, if possible, to be built in Sweden. Swedish industry formed two new companies, and the present Saab, the Swedish aircraft industry, was formed 1939 with headquarters in Linköping. The need for new military aircraft increased rapidly when war became imminent. And the Swedish Air Force tried to purchase aircraft in Europe and United States. Most orders were eventually cancelled. In the meantime, Saab increased its resources for production and design as fast as possible, partly with the help of designers from the United States. In 1940, due to the war situation, most contacts and imports from outside war was broken, and the aircraft and engine industry was left on its own. During this period of isolation, a complete aircraft and engine industry was built up with Swedish subcontractors of material, equipment to instruments. Aircraft quality standards were introduced at all suppliers. Design and testing technique, as well as method for calculation and analysis, was learned. A new generation of capable engineers was educated. At the end of World War II, the Swedish aircraft and engine industry was ready to benefit from all the new technology which was developed by the countries involved in the war. For example, jet engines, high-speed aerodynamics, missiles, and electronics. Supporting the industry, the resources for research and technology development and education was gradually built up at our Defense Research Institute, the Aeronautical Research Institute, and our universities, mainly the Royal Institute of Technology. After the war, Sweden did not reduce its armed forces. Instead, as a result of the Cold War, earlier plans to increase the strength of the Air Force were retained, but now with new technology. The background to this decision was the lesson learned before and during the World War II. We wanted to stay out of wars and therefore stay neutral. But this neutrality had to be defended by strong defense forces based upon internally developed and produced defense material. A series of fighter aircraft of high quality and with performance of high international class was produced after the war in quite large numbers. The last one was the Viggen aircraft, and which the last example was delivered earlier this year. During the 50s, the scope of the industry was broadened to include system analysis, electronics of all kinds, missiles, and later space products. The present situation is such that the willingness of our parliament to allocate increasing sums of money to defense has gradually decreased. Since the middle of the 70s, defense spending has decreased in real terms, and the strength of the armed forces has also decreased. This trend seems to continue, not least due to the reduction of tension between the superpowers. The political discussion about a successor of Viggen, our last fighter, was therefore very arduous and took a very long time. The question was, could we really support the idea to build aircraft of domestic design? It came, however, to a positive decision at the beginning of the 80s, mainly due to two circumstances. We were able to offer a new military aircraft which was much smaller than the Viggen aircraft and which broke the trend to ever-increasing cost, and that was the JAS-39 Gripen. We also promised to increase the civil portion of work in the industry, and in this way decrease the burden for the defense. and Saab Scania launched a new regular aircraft, the Saab 340, which is now being followed by the larger Saab 2000. The program has been a great commercial success. Volvo Flygmotor has entered a large number of collaborative programs for new jet engines for civil aircraft. Well, a short word about aeronautical spin-offs. Among the arguments used by the aeronautical industry to continue to expand aeronautical programs in Sweden is the spin-off effect. Aerospace is a high-tech area which will help to strengthen other industries and the economic development of the country. Numerous investigations have been made to throw light upon the spin-off effects, but without great success. At least our politicians have found it difficult to credit the spin-off with much significance. My belief is that the greatest value for society of high-tech work is that it creates a need for advanced research and advanced education, and that young, well-educated engineers become available for all the industry. The justification for aerospace industry is therefore solely based upon the value on its products. The Swedish Aeronautical Basic Research is carried out at the Aeronautical Research Institute here in Stockholm, at the Royal Institute of Technology and other universities and industries. The volume is rather limited. It is funded mainly by the defense. Also, a contribution is provided by the Swedish National Board for Technical Development. We are therefore very dependent on the flow of information from abroad. We wish to belong to a free scientific community in which scientists cooperate closely and communicate information and reports freely. Congresses like this one are of great importance for us. We have with some fear noticed the trend, especially among the major nations, to put restrictions on the free flow of scientific knowledge. The research result, which is collected from many sources, is transferred to methods and knowledge of direct interest for our development work, by which we call technology development. The main part of these takes place in the industry and is financed by the industry and to some degree by the defense. We have noted that the European community in one of its research programs has initiated cooperative research and technology development in the field of aeronautics. We are extremely enthusiastic about these programs and will take part in them, even if we have to pay all the costs ourselves. It should maybe also be mentioned that the aeronautical research institutes of the European countries are discussing coordination of their programs. Much has to be gained by each country if such cooperation is to come about. ICMA, the European Aeronautical Industry Organization, has started to list all the test facilities in Europe as a basis for collaboration in the future. As outlined above, Sweden has succeeded in building up and maintaining an independent and complete aerospace industry with capabilities in airframes, engines, equipment and electronics. More than 50% of the products are now intended for non-military use. It is true, however, that our products are not any longer pure Swedish. More and more material, parts and subsystems are being imported, mainly for economical reasons. In the case of civil aircraft, we have tried to involve foreign companies as risk-sharing partners. I believe that in the future we will have to extend international cooperation both in the military and commercial field. Perhaps we have to form some kind of more permanent cooperation with foreign firms having similar profiles and ambitions. Possibly we should form a consortium of companies for regional aircraft smaller than those of Airbus Industries are working on. Quite a number of regional aircraft types are now being offered on the market. and very few of them will show profit in the end. It is interesting that modern information technology will make cooperation easier in the future. Drawings made by computer-aided design, defined in digital form, can easily be sent to other companies via satellites or by optic cables. That is true also for other data which is necessary for manufacturing and maintaining of aircraft. But the electronic information system in the different firms has to be compatible with each other. Icas, the industry organization, has identified this problem a long time ago and has now formed a standing committee for electronic data interchange. I believe this is a very important step. Another condition for cooperation is the free labor market for engineers, in that technical degrees in different countries are well defined and coordinated and also accepted all over Europe. Progress in this direction has been made in the European community, even if all the problems not seems to have been solved. The ambition for Sweden is to retain our system capability to define, assembly, complete aircraft, and even with a new cooperating structure. I will end with a few comments about our latest aircraft. In the aeronautical world, everyone knows that we had an accident with the first prototype of the Gripen and that the second prototype is now flying. First, I want to state that the performance of Gripen, as far as it has been tested, meets the specifications. The configuration is right. The concept of building a small aircraft to reduce the life cycle cost is sound. It is an aircraft for smaller nations with a limited defense budget. To reduce weight and cost, we decided to integrate the digital electronic system as far as possible. Unfortunately, we underestimated the volume of software work, which caused delays and caused overruns. The software of the fly-by-wire system was not fully tested when we started to fly, and that caused the accident. Even if the highly integrated system has advantages when ready, it has disadvantages during the testing period. A fault at one point in the system influences a large part of the rest of it, and the fault detection is also difficult. I mentioned that our civil aircraft program has been a success. The Saab 340 with 34 passengers was intended as a feeder liner to big airports. The Saab 2000 with 50 passengers has a higher speed and longer range and will be used for point-to-point traffic outside the big airports. The biggest threat to our market is the saturation condition at the major airports and the limited capability of the air traffic control system. If the traffic movements are limited and the traffic continues to increase, then this increase can only be met by using larger and larger aircraft and not our small aircraft. It is therefore essential to eliminate the limitation of the airports and airspace, which only can be done with the help of new advanced equipment and modern information technology. Unfortunately, this will take a long time due to the bureaucratic decision procedure, limited cooperation between nations, and the high investment costs. If we do not solve the problem, however, quickly, passengers will be faced with increasing delays in overcrowded airports. We are indeed happy that this conference is taking place in Stockholm. The Swedish aerospace community is not a large one, but has a great deal of know-how. We have a good range of products and services. Our philosophy for the future is to be even more international and seek cooperation abroad. New, long-lasting forms for such cooperation has to be found. Thank you for your attention.
Presidents, Excellencies, distinguished guests, ladies and gentlemen, on behalf of Icas, I most cordially reciprocate the welcome wishes to the host society of our Congress. We are very glad to be invited by Sweden. Its aerospace involvements are, as we just heard from Mr. Gullstrand, impressive. Its products in this field are amongst the leading ones in the world. I'm very glad that within the Swedish society, we always had committed friends who fostered the aims of Icas. I want to express my sincere thanks for the beautiful and efficient cooperation we had during the preparation of this conference, first with Sweden's Icas representatives, Dr. George Struge and the late Dr. Stig Lundgren, and later on with the Society's presidents, Dr. Lilja and Dr. Lars Andersen. The development, establishment and operation of a well-functioning and safe network of air transport to all points on our Earth belong to the great tasks of man. It is still a challenge today. We all are aware that it required, and it will require even more in the future, multinational efforts and individual collaboration. This is why the aeronautical societies, taking their share of responsibility as essential instruments for the transfer of skills and knowledge between experts, have joined in the World Federation, which is the International Council of the Aeronautical Sciences. It integrates now 31 countries from all 5 continents, and it is expected that after our meeting here, 2 more will become partners of our community. Those are Pakistan and South Korea. Both have recently applied for membership. Icas is proud that it is a prime international forum for the exchange of ideas in aeronautical sci-tech, irrespective of national borders and political constraints, and this since now more than 30 years. It was therefore very embarrassing for Icas, having been confronted here in Sweden the first time in its long history, as a well-renowned international organization, that the host country has refused visas to bona fide delegates to attend our scientific congress solely on ground of nationality. Icas will take all appropriate measures that future congresses will be held only in those countries which will guarantee free access to our conference to any respected delegate. I very much regret to say this, but I'm afraid that the unfavorable government decision will cause alarm and second thoughts in the councils of other international scientific bodies. Communication between scholars, scientists, and engineers is a vital means to accelerate technology. We need it to improve the living conditions of people. To present one's own new findings to an expert audience and to publish them is essential, as we all know. It is productive for the individual, but it is also beneficial for the public, which is entitled to get informed about that what we are doing. Investigations will show that scientists and engineers who present their results instead of holding them back for whatever reason can expect incomes which may be by 30% higher on average than if they remain silent. But 75% of all publications are written by only 25% of the ensemble. Knowledge which is kept in the desk is lost knowledge. Publish or perish, this is very true. Icas feels very satisfied that its call for papers has attracted a very large response. More than 450 abstracts had to be screened by the program committee, a formidable and responsible task indeed. But Icas feels also very sorry that only 250 papers could be kept for the final program. The rejections were not based on quality alone. Most papers were of excellent standard. Other criteria like good fit into a session or avoidance of too much overlap of two similar papers had to be applied. May I thank, therefore, the program committee, and in particular its chairman, Pete Peterson, director at NASA Langley, and Professor Alec Young, our executive secretary, for their great effort and their excellent success. But this is something what has to be judged by each participant, that means by you himself. I want to extend my thanks to all the authors and co-authors, but especially also to those whose papers have not been selected. They also contribute in a very essential way to a good program, because they give us a choice. Air transport itself may be considered now, besides education, as the largest contributor to world economy. Its influence on the civil and cultural development of our societies is evident. Quick and widespread distribution of messages and goods, individual mobility as an essential aspect of personal freedom, keeping up personal contacts over continents, handling business by meetings on whatever day and in whatever place, fast transfer of meeting results into decision-making processes, work sharings over large distances, acceleration of cultural exchange and interaction. I believe those are goods which cannot be appreciated enough and which have become a must for the welfare of people. During the recent years, we clearly could observe two trends. The traditional strong transatlantic exchange in economy over the mainland of United States up to the West Coast has been supplemented by the Trans-Pacific as well as by the European East Asian one. The growth rate is breathtaking. Naturally, one factor is the powerful economy of Japan and of the little tiger countries. Another one, however, is the tremendous population potential of the Southeast and East Asian region, with an impressive economic growth. More than half of the world population is living in that area. The second observation is a surprising increase of long-range tourism. Tourism itself is shown to be the worldwide largest industry, with around $2 trillion sales and with 100 million employees. This corresponds to a gross world potential of 5.5%. We now can gladly envisage a third aspect. The dramatic changes in the relations between the East and the West gives us new hopes that people of both political hemispheres will become much closer to each other by personal contacts, by economic relations. There exists only a very weak east-west ground traffic infrastructure to transport goods and people at present. It inevitably will become a task for aviation to a great extent to provide the transport links needed. All those factors imply the demand for higher transport capabilities, either by enlarging the fleets by aircraft number or size, or by increasing the block velocity. Mr. Gullstrand has already made reference to it. That triggers new considerations how future air transport will look. Will it be sufficient to stay with the present families of narrow and wide-body aircraft, or do we expect new developments, perhaps of revolutionary type? We all are aware that the sky has become narrower. In highly populated and highly developed areas, air traffic control has shown to be the constraining factor of aircraft operation. Instead of moving towards a still higher air traffic density with more airplanes, many governments have taken the decision to improve ground transport by rapid trains like the CGV or the Intercity Express, or by completely new transport systems like the magneto-hovering vehicle with speeds up to 400 kilometers per hour or even higher. For short-range operation, this may give some relief. For long range, this will not be the case. Already Küchemann has suggested in his book on aerodynamic design that journey times which exceed, say, 2 or 3 hours are not favorably accepted by the passenger, and he tries, if he can, to avoid them. Two solutions to give the passenger some relief for large distances are being discussed today. One suggestion is a sleeper aircraft. It gives more comfort and makes a long trip more bearable. It contains the usual conventional features. It is, however, associated with a different internal layout of the location of convertible seats, and it may require the usage of space which is nowadays occupied for cargo purposes. It requires possibly some new deliberations for the proper application of airworthiness requirements. The other option should allow some thoughts on the feasibility of a supersonic transport associated with all those adverse aspects related to noise, sonic boom, pollution, depletion of the ozone layer. There are also serious arguments who state that business traveling will be reduced in the future as soon as video conference switching will be widely available. But there are good points to say that video conference meetings cannot replace personal contacts. They will be expensive and can be afforded only by the same people who otherwise would fly. I could rather think of a scenario in which businessmen will fly to meetings and use video conference equipment just to get linked to the home base and to the staff. Recently, it was jointly stated by representatives of major aircraft companies at different conferences and air shows that the capacity of the aircraft manufacturers for wide-body and middle-class narrow-body aircraft is not sufficient to satisfy the increasing demand of the airlines in good time. By the year 2005, aircraft orders for more than $500 billion are to be expected. The main aircraft manufacturers have announced an enlargement of their production line. Just last week, around 200 high-capacity passenger aircraft for $14 billion have been contracted at the Farnborough Air Show. The two most important innovative landmarks in the past of civil aviation may be attributed to the implementation of jet engines and swept wings for transport aircraft. This was achieved over 30 years ago. Both features are still decisive for the shape and function of modern civil airplanes. Naturally, there were other innovative achievements of great importance and impact on aircraft layouts, such as composites implemented in primary structures, supercritical, transonic, vortex-dominated wings, active controls, all-electric aircraft, advanced cockpit display, very high bypass engines, and some others more. Those technologies have given together incredible new performance and incredible new safety standard. Engineers and scientists are doing a marvelous job to improve flying. The program of our Congress will be a beautiful proof. It will show that most disciplines can demonstrate impressive progress. However, any technological advance for a still superior aircraft, leading to higher performances, lower drag, less weight, reduction in fuel consumption, less work imposed on the pilot, is counteracted by the present bad situation associated in airports. An investigation of an international flight traffic users bureau published last year in 1987 and 1988, the portion of late flights has tripled. Some European routes require sky. The costs involved by those 88 amount to $5 billion, around 150,000 to the total capacity of airlines like Swiss Air or Dutch Airlines. One should have in mind that the trade-off for the profit or 2% of the fuel consumption or some 10 counts of drag of its fleet. What means then improved performance for an aircraft achieved by most sophisticated and the airline is now directed towards a supersonic or Concorde plays the role of a brilliant avant-garde. The Concorde fleet has achieved more supersonic flight hours than with supersonic capabilities. The Concorde has unique value for realization of a civil supersonic transport. It could have, however, also its value for opening flight regimes going beyond. It's a challenge to the engineer of taking over tasks in the past, and they have solved them even when the tasks were in principle too difficult for them. They solved them in advance of the scientific substantiation, not in their wake. The Strasbourg Symposium on supersonic aircraft, which has been prepared jointly by the French Academy, the German Aerospace Society, and the Royal Aeronautical Society last year, has clearly shown that several leading airlines support the idea of a supersonic transport. The crucial issue is the impact of such an aircraft on the environment. It is a renewal of the heavy discussions which have been held 28 years ago, also on the occasion of an Icas Congress, also here in Stockholm. At that time it was a Concorde which was judged very controversial, and it was your Swedish countryman, Bo Lundberg, who made the Philippica. For the future supersonic transport, it might be possible to surmount the noise problems by the use of advanced engines designed for supersonic flight. There might be engineering solutions to handle the sonic boom, possibly by sophisticated configurations or by shaping the boom signature. The big unknown now is the depletion of the stratosphere by nitroxides directly or by catalytic processes, with all its consequences on the ozone layer. Even hydrogen as a propulsive fuel seems not to give a safe answer to this question. We should also keep in mind that the exposure to radiation of passengers and crew would increase due to the higher flight altitudes. Only a solution which is a responsible one and which is favorable to the public can and will be accepted by the human society. It has to be a very cautious approach toward such an aircraft. I could think of a worldwide effort, including 3 continents, to develop just 1 or 2 prototypes first, which because of the small number would not mean a hazard, but with which the whole spectrum of envisaged and unforeseen problems could be studied thoroughly and possibly brought to an acceptable solution. We are sure this Congress will help us tackling many or maybe some of those issues mentioned. Let me remind you in this context of Bert Brecht, the famous German writer who makes Galileo Galilei say, "Who is him who does not search but nevertheless speaks about?" And I think too many don't search and speak about. Ladies and gentlemen, we are all looking forward to a successful Congress, to a very successful one. Thank you, or as it is simply said here in Sweden, tack. We now will not have really a break, just 5 minutes to change seats if necessary. Those who don't want to change seats, please remain seated. We will start afterwards with the Guggenheim Memorial Lecture. Thank you. So would you like to take your seats, please? Distinguished guests, ladies and gentlemen, it is one of the privileges and obligations as well of scientific societies to honor personages who have markedly contributed to the development of knowledge. Icas serves this purpose by bestowing 3 awards, each one with different objectives, namely, first, by the invitation to hold the Daniel and Florence Guggenheim Memorial Lecture in the Aeronautical Sciences. The aim is to treat with distinction an outstanding scientist, a person who has set landmarks by his own research work. The lecture to be given in this context should review the state of the art in the field of his personal engagement. Since the first Icas Congress in Madrid in 1958, the lecture is a highlight of the opening session. Second award is the Icas von Kármán Award for International Cooperation. The aim here is to acknowledge an outstanding multinational program that can be either a scientific, a technological, or an engineering project. The award has been introduced first in 1982. It will be presented at the closing ceremony of our conference. Third, by the Maurice Roy Medal in memory of the great French scientist and former Icas president. It will be endowed second time at this Congress on the occasion of the banquet on Thursday evening. A personage of high reputation with exceptional merits in international collaboration is to be selected. Now, the Guggenheim Lecture is closely related to the existence of Icas itself. This is because Harry Guggenheimer, the noble American industrialist, philanthropist, and sponsor of science and arts himself, initiated our worldwide federation. He funded the first meeting of representatives of 9 aeronautical societies who convened January 29th in New York to create Icas, and Sweden was among them. It was a breakthrough after World War II to restore the confidence between scientists captured in the ideological environment of their own nations. It is now a great pleasure for me that Martin Theodor Landau, Dr. Technology, Professor of Aeronautics and Astronautics at the Massachusetts Institute of Technology in the United States, formerly professor at the KTH, the Royal Technical University in Stockholm, will give us the honor to present the Guggenheim Memorial Lecture, CFD and Turbulence. The understanding of turbulence seems to have remained the last white spot in classical mechanics. It is an unsteady three-dimensional flow phenomenon which occurs even when the free flow and solid surface boundary conditions are steady. Numerous papers have dealt with this subject with more or less success. Turbulence modeling still belongs for many of us to the most mysterious matters. We know of algebraic models, we know of differential equation models, we know of coherent structures of turbulence. We believe that the Navier-Stokes equations could give us a full answer if CFD would allow a resolution from large eddies down to very small ones. Professor Landau has tackled this sophisticated problem since years, and we surely will be fascinated about what he has to tell us. Professor Landau studied at the Royal Institute of Technology, KTH, Stockholm, where he also received his doctor's degree in 1956. 1960, research scientists at the Aeronautical Research Institute, Sweden. From 1960, Associate Professor, Department of Aeronautics and Astronautics at MIT, 1963, Full Professor at MIT. From 1967 till 1988, Full Professor for Mechanics here in Stockholm at KTH, and now back to MIT. Professor Landau's achievements are too many to mention them all. He contributed to so different fields as wave mechanics and aeroelasticity, steady and unsteady aerodynamics of aircraft components, wind energy and gas centrifuges, acoustics, ship hydrodynamics, geophysical fluid dynamics, vortex flows and rotating flows, and last not least, to flow stability and turbulence at all. I surely have forgotten some of your fields. Nearly 100 publications in renowned journals are vivid testimonies for his creative power. His monography on unsteady transonic flow may be found in any library on aeronautics. It is obvious that Professor Landau has been widely honored for his manifold and important scientific work. I'm mentioning only 2 awards: the Tulin Medal for his contributions in the field of aeronautics, bestowed by the Swedish Society of Aeronautics, our host, and he was selected by the 2 German societies of aerospace and of mathematics and mechanics, respectively, to present the 27th Ludwig Prandtl Memorial Lecture. I think it was in Regensburg. Professor Landau, it will be a great pleasure for us to follow your lecture.
Thank you very much, Professor Laska. Professor Laska's and my paths crossed many years ago when we were both interested in unsteady aerodynamics, in particular unsteady aerodynamics related to aircraft flutter. Now, as you can see, Professor Laska has moved on to more important tasks, whereas I am still involved in calculating unsteady flows, now looking at the most unsteady flows of all, namely turbulence. Dr. Gullstrand reminded me of the early developments in Sweden of research and development, and I'm afraid he left out one of the most important part of that of all, namely the role that the aeronautical laboratory of the Royal Institute played. This was a laboratory built up by the Professor Sten Luthander at the time, and Dr. Gullstrand had a very great role in this laboratory. And I remember the many, many discussions we had at the time, and which inspired all of us, and I think without exaggeration I can say that practically all of the leading engineers and scientists in Sweden in the field of aeronautics emanate from this particular laboratory. Professor Luthander, he was very foresighted in getting hold of some of the most prominent scientists of the time in the area of fluid mechanics. Professor Osvatich was one, perhaps the most well-known one, but he also, at the time when I was there, which was early 50s, he had a German scientist by the name of Dr. Ries, I believe, who had the idea that you could solve the partial differential equations of fluid flow by direct numerical integration, finite difference approximations and the like. And of course we all scoffed at him and laughed a little bit at him. I know a great deal of what he was thinking about because I was sitting in the same room as him, and he was working on the only tool available for him at the time, namely a non-electric typewriter, and he produced a lot of writing on this subject. And of course, after a while he disappeared to greener pastures. And after that time, of course, there has been a tremendous development in the use of computers in fluid mechanics and engineering. And for my own doctoral thesis, I used one of the first and very fast electronic computers built in Sweden, who occupied a floor area of about this hall, and with that many electronic tubes that could go wrong, nevertheless I managed to evaluate a series of 1 million terms to agree with a asymptotic theory of mine, which was very useful for me, and which still can be read about in my book. Now, what I wanted to start with here is an overview or a table of contents of my talk, and so that those of you can follow the suggestion of one of the speakers here that most of the work may be slated for the drawers in your desk, and some might be of some value in the future. The task, of course, for an unsteady aerodynamics is a computation of unsteady and chaotic viscous flows, which is turbulence. The tool, computational fluid dynamics, known as CFD among the people in the crowd. The technique, direct simulation or modeling of turbulence. We learn about turbulence physics, and this is what I'm going to stress: transition and fully developed turbulence, both. I'll say a little bit about the trends, changing roles of experiments and analysis in the field of turbulence. And finally, I come to some tentative conclusions, and the conclusions are tentative not only to not to spoil the alliteration here, but also because there is such a rapid movement in the field of the use of computers. What is a computational task one is faced with in computing turbulence? Well, one has to look at scales. The largest scale may be the scale of the body, aircraft, or whatever, or one might be satisfied by using as a larger scale the thickness of the boundary layer. Now, the smallest scale is something which was worked out by Kolmogorov a long time ago using simple theory, and he found that the smallest scale relates to the largest scale as the Reynolds number to the minus 3/4 power, where the Reynolds number, of course, is defined in the usual manner. Now, there have been some later developments in this field. Perhaps the smallest scale is a little too conservative in the Kolmogorov estimate. Henshaw and company, which includes Heinz Otto Kreis, who is a famous mathematician in this field, found that the smallest scale perhaps rather is proportional to the Reynolds number to minus 1/2, where the Reynolds number now is based on the largest rate of shear in the flow. The only problem with this estimate is that you cannot make an a priori estimate of the maximum of the shear rate in the flow. The only case of turbulence where this is possible is in two-dimensional turbulence, and in which case one can save then a lot of computation. And two-dimensional turbulence, although it may sound uninteresting to engineers, is of some interest to geophysical fluid dynamicists because turbulence controlled by rotating flows tends to be two-dimensional. Now, the time scales can be related then directly to the scales of the body, or the shortest scale, and relates to in the case of the shortest scale, which is the important one, is proportional to the Reynolds number to minus 1/2. Character of the flow is random, unsteady, and chaotic. And you may have read and heard a lot about the ideas of chaos applied to turbulence. Some physicists appear to think that just by mentioning the magic word chaos, all the turbulence problems are solved. This is not so. But one thing we have learned from the ideas of chaos is that the flow is extremely sensitive to initial conditions, so that if you compute two different turbulent flows that differ just a little bit in the initial conditions, the detailed flow is quite different. And of course, one is not interested as engineers in the detailed flow, perhaps, but rather in statistical averages like average skin friction, for example, and transport coefficients like heat transfer and the like. Now, computational techniques. It takes a little bit of reading here. I hope you have your. Oops. Oh, there we are. Your good reading glasses with you. First of all, you have to generate a computational grid, which means divide up the space in suitable small portions. It can be a grid that looks like a raster, or it could be a grid which contains embedded meshes and several different grids, depending on what area of the flow that is most detailed. Then after that, one applies finite difference approximation or finite volume or spectral approximation to the spatial derivatives. And then one computes steps in times. One goes on with time stepping until one reaches a steady state. Steady state, of course, in case of ordinary aerodynamic problems, but in case of turbulence, you have to reach a statistically steady state, which requires perhaps that one has to let the computation run 10 to 20 times the time it takes for a significant eddy to turn over. Then comes a very important part of the problem, namely post-processing of the results, visual display. One doesn't read any tables anymore, but one looks at pictures, and the pictures are usually colored. One uses statistical analysis, and I show some examples of that later on. Computational times needed is a very important question here. The time is set by the fact that you cannot use more than a maximum time step because of stability, numerical stability considerations, and that is determined then by the spatial discretization, and then one can work out various times here. Steady flow might require some 1,000 iterations to reach steady or convergence, and for uncomplicated aerodynamic configurations that may require minutes of computation. What is perhaps more fascinating and interesting from basic science point of view is a direct turbulence simulation where one can work out an estimate of the time is proportional to the Reynolds number to 11/4 power times logarithm of the Reynolds number. And if you want to look at a simple channel flow, say Reynolds number of 100, it's a question of minutes. For 1,000, it's a question of hours. Now you're beginning to burn the people in the economic department. And then you go up to 10 to the 4th, it's like years, and 10 to the 6th, it's like never, at least for people of my own age class. So one can begin to see the limitations here. Now here is an example of a steady flow calculation that I borrowed from the Aeronautical Research Institute, and which takes something like minutes to compute, and it's a nice picture because of all the nice colors. Some people suggest that CFD shouldn't stand for computational fluid dynamics, it should stand for colored fluid dynamics. This is a good example, and this is a flow wing with separated vortices, and one can see both the main vortex and a secondary vortex in this picture. And I give this example as a contrast to the kind of precision one can predict the behavior of transportation that goes through that of what you saw yesterday evening with the Vasa, where one did have difficulties in predicting the metacenter height of the vehicle. Perhaps one didn't want to at the time. Anyway, things have changed. Now, I like to show a couple of simulations and comparisons with theory and other kinds of computation calculation. First of all, what one would like to do with a simulation like this is to have something that you can compare with that you trust, because the computation may or may not be correct. And in case of things related to turbulence, one can compare with transition with instability mechanism. Instability mechanism in shear flows are pretty well understood. This is now a comparison with a instability wave in a channel flow. This done a couple of years ago by Fasel and his student Bestek. And I should use this. Doesn't get any better. Well, the results are not that accurate anyway. But The comparison that's interesting is in the top graph, where you see the increase in the maximum amplitude with distance downstream. This is computed now for a wave-like disturbance, and you see here with the dotted line is linear theory, and with the solid line is simulation, and you see two different values there of initial conditions, and there is pretty good agreement between the two, which makes you trust the calculation. And of course, in the bottom picture, you see then just a display of the streamwise perturbation velocity. Of course, that's a more or less sinusoidal. It's sinusoidal in time, and therefore it's practically sinusoidal in space. And of course, that's useful for the numerical analyst, because in setting up a calculation like this, you have to work out a suitable computational box, and you have to say something about what do you put in for the ends of the box, upstream and downstream. And here you can say that the flow is almost periodic, and therefore quite easily represented by a couple of wavelengths. Now this is now a simple calculation in that case, in which one could compare directly with simple linear theory. Here is a much more complicated situation in which the people involved, Orszag and Patera, Patera the student and Orszag the professor, worked out the instability of a finite amplitude and a two-dimensional steady state instability wave, and looked at perturbations of waves that were in oblique relative to the primary wave. And this is now the growth rate. Sigma is the growth rate in time plotted against the angle with respect to or rather the wave number with respect to the crosswise wave. And as you see here, this is now linear theory based on linear perturbation of the finite amplitude wave, and these are two sets of simulations done in two different ways. And as you see already here, one can find some, or see some more interesting physics in the problem, namely that the two-dimensional wave has three-dimensional instabilities that grow by themselves. And of course, turbulence is highly three-dimensional, and the interesting part of instability theory is to see how three-dimensional disturbances develop out of a two-dimensional flow. Here is almost a very bad focal here. Could you please focus a little better up there? Well, yeah, thank you, thank you. Here is a simulation of a two-dimensional, initially laminar flow in a channel in which a wave-like perturbation was introduced and followed through until the flow became more or less turbulent. You see here different time sequences, and in the lower portions, time t equals 300, it's about as turbulent as you can imagine the flow is. Of course, one would have to look a little bit at statistics to determine whether this is truly statistically steady in the turbulent sense, but again, it indicates a bit how the flow does develop by itself. And I'd like to show now a picture of a flow that's also worked out in this way, but starting from different initial conditions. In this case, a point disturbance was introduced, and the flow then was followed. This was done by my former student, Don Henningsen, on the computer at NASA Ames Center. And what you see here is the development of what is known as a turbulent spot. A turbulent spot is a region of turbulent flow that spreads and contaminates the flow around it. And what is interesting here from the basic point of view are the wave fronts you see at the edges, the wings of this spot. Now there is a little bit of cheating in this picture because he really only computed half of the flow, assuming that the flow was completely symmetrical. Of course, that's a foregone conclusion in the case of a chaotic flow, because if you'd computed the whole flow, maybe the two sides would have looked a little bit different. But anyway, this was a limitation of the amount of computer hours they gave him at NASA Ames, which are a couple of hundred in this case. And in fact, the presence of the waves could be verified by looking at the mean velocity taking away the wave disturbance and looking at stability of that portion of the flow, and indeed it was found to be unstable, and also a separate investigation could be shown that the wave propagation was such as to favor waves of this kind here. Now, let me now come to a subject which is now of great interest to engineers and aerodynamicists, namely modeling. I also include here statistical closure. Statistical closure was something that was worked a great deal by a lot of famous physicists, including Heisenberg, for example, who then gave this up because he had easier problems to work on. The reason for modeling, of course, is that you cannot afford to compute the full unsteady, detailed, turbulent flow, but you have to make some assumption of how the small scales relate to the large scales. Also, in the case of closure models, one can look at the statistical treatment of the Navier-Stokes equations and find then that the number of equations always is less than the number of unknown statistical moments, and therefore one would have to make some assumptions about how the higher moments relate to the lower. And I'll start with that. There has been a great deal of work by a man called Krishnan. His first effort was called direct interaction model. And there have been a lot of improvements of that, adding to the number of letters in the description of the method. Here we have E, D, Q, and M, which stands for eddy-damped quasi-normal Markovian. I am not going to describe in detail what that means, but the man Orszag has worked this out. And the interest with direct simulation is, of course, that now one can try these models out with direct simulation and see how well they behave. And here's an example of this. This is a calculation carried out by Orlando in Rome, but working at NASA Ames. And you see here the spectrum of the energy transfer, which is a nonlinear portion of the statistical analysis, which is the clue or the crucial part of finding a appropriate closure. And as you see here, the E, D, Q, and M, which is unfilled squares, looks pretty good compared to the direct simulation. So here you see a usefulness of the direct simulation on the fundamental point of view for understanding the statistical nature of turbulence. Now here is another one in which a different modeling has been used, and let me just go back to slides here just to tell you about the different turbulent models that have been tried. The simplest one is one suggested by Boussinesq in the last century, simply replacing the ordinary viscosity by turbulent viscosity. Prandtl suggested using something called a mixing length hypothesis, which simply meant letting or assuming the fluid elements to retain their horizontal momentum as they move around by the turbulence. And actually, I've looked from a theoretical point of view at that model, and it's actually pretty decent from the physics point of view. Then there are more complicated models involving differential equations, and the most well-known one is the so-called K-epsilon model, which is incorporated in many of the commercial codes that are available for turbulent calculations. Large eddy simulation is something first introduced by Smagorinsky in the meteorological calculation field. He assumed that you could model the smallest scales by some simple eddy viscosity or simple viscosity, and with that could concentrate the full simulation on the large scales. And I like to show you a comparison of the direct simulation, which is the top picture here of the flow in the late stages of transition in a channel flow with large eddy simulation. And the character of the flow is pretty well retained by the direct simulation. In particular, you see the formation of strong internal shear layers, and I'll come back to these a little bit. And this is span-wise vorticity, and here you see also these thin shear layers occurring very near the wall. This is very typical of turbulent flows, and can in fact be explained with a very simple model, which I've sketched here freehand. If you assume a flow that is completely passive, there is no vertical velocity perturbation and no pressure, then a streamwise velocity perturbation called U here simply says that the rate of change following fluid element moving in the mean velocity field should be 0, and you can solve this directly in terms of a Lagrangian variable psi, which is x minus u of y times t, and this is nothing but a hypothesis introduced by Taylor a long time ago. He called it the frozen field hypothesis, namely that the field follows simply in the frame of reference moving with the mean flow. And when you work out then the shear, the perturbation shear due to this frozen field, you find one term that has a term which is proportional to time, and then there's another which is not proportional to time. So after a while, the shear increases, and it's taken over primarily by this term, which is really simply a consequence of this whole area that is disturbed being sheared over by the mean shear. And one can, in fact, explain it also in terms of the vortex stretching of the mean flow, so that one would expect any turbulent shear flow to have regions of shear like that embedded in the full turbulent flow. Now, one has made numerical simulations of plane shear flow also. These are results from looking at a concentrated shear, in other words, a free shear layer, the contact of two regions of velocity of different velocities, and what one knows from simple stability theory is that there is an instability mode developing like a wave, but the wave then rolls up and produces rolled up vortex cores, and the cores themselves pair, some marriage of neighboring vortices, and all of this can be studied very nicely with numerical simulation. It's more difficult to see in the laboratory, although that has been done also. But of course here one can look at things in much more detail. Here is what happens to these rolled up vortices as they progress in time. They form braids of three-dimensional vorticity enhancement, so that there is the development of a three-dimensional instability that tends to have a certain scaling in the span-wise direction. And some people have suggested this is related precisely to this three-dimensional instability that I showed you results from in the beginning. Now, do these shear layers occur in a fully developed shear flow? And the answer is yes, and here I have borrowed from calculation by Icas. This is so new that I can't give you a reference to it in a written paper. But what you see here is the span-wise vorticity, and you see how this develops as function of time is followed on the computer. This is done in Lausanne at the École Polytechnique Fédérale de Lausanne on their Cray 2. And these are very detailed calculations. Actually, the shear layers here are much flatter than it appears on this picture, because in order to see what's happening, he has expanded the vertical coordinate by a factor of 2.5 or so that think about this as flattened down more than you see here. But what is typical is that you see this wave-like disturbance developing, and in fact, the shear layer breaking up into such clumps of shear. And this is very typical of turbulent flow, that the shear or the vorticity tends to be very clumped. Well, now I come to say a few words about, can we replace the laboratory by computers? And there's been a great deal of discussion of this lately. And the question is then, what can we do with using the computer as an aid or as an experimental tool itself? Of course, we have seen already verification of theory. One can calibrate computer codes, because one doesn't necessarily know that the computer codes are correct. In fact, I think one should always assume that the computer code has errors in it and look for the errors. One can test models, closure hypothesis, as we have seen. One can use statistical analysis of turbulence data banks, and from that studying turbulence physics, and I have some results towards the end here to illustrate this. First of all, this is a analysis of computer simulated turbulence done at NASA Ames by Robinson, where he has looked at regions of low pressures in the flow. Of course, there is no way you can measure instantaneous pressures inside the flow. So here, the computer is practically the only experimental tool you can use. And what you see here is this clumpiness of low pressures, which indicate that there are small, strong vortices there that act like tornadoes having low pressures inside them. Now, you don't see so much in this, which is just a cross-cut looking at it from above, but one can do a little better by making use of color coding. And here is low pressures indicated by white. Here are some velocities, correlation of velocities indicated by blue, and vorticity by red here. And you can draw some conclusions regarding how the two are linked. But it is still very difficult to get a sense of what is the cause and effect in this particular kind of instantaneous flow situation. Now, you look at the flow near a wall from a very short distance from the wall. This is now at the distance. I should remove that tape from the screen here. That's irritating. You see a flow which is dominated by a streaky structure with high and low pressures, high and low velocities. Streamwise velocity pressures are not high and low necessarily. And this is now a computer simulation in a region at the distance of y plus, which is a measurement in terms of Reynolds number based on the shear velocity and distance from the wall. It's very, very close to the wall, and you see this streaky structure. And the question is, can one explain this streaky structure? Now, one can do some analysis of more of the data banks that have been generated by these simulations. And the top here shows a analysis done by Alfredson and his co-workers, also at NASA Ames, in the summer program they have. And here they have used conditional sampling called VISA sampling, which stands for Variable Interval Space Averaging, which means that you average over a certain preset space, and you see when the difference between the long-time and the short-term average of squared quantities is the largest, and then you say then something happened, and you have those times then determined by this method, and then you can make averages around this time, and this is now time t equals 0 in this particular case, and you see now there's a high-speed region here and a low-speed region here, separated by a shear layer at the particular angle here, which is very small, like 5 degrees. Now, I've done some simple theory on this, and the result of the theory you see below, which is essentially based on something that the experts call rapid distortion theory, which is a little more sophisticated. And you see that the simple theory, which can be evaluated by a desktop computer actually, is pretty good in its qualitative results. I have one more such result. Here is looking at such structure from above, making sure that the asymmetry, the span-wise asymmetry, is retained, and you see then that the high-speed region gets sort of a kink here, and the low-speed region next to it also gets sort of a kink, and the simple theory seems to follow this trend also pretty nicely. And it turns out that the mechanism involved is again not the usual one in classical instability theory, but one which I call algebraic instability, which grows linearly in time and therefore tends to dominate near the wall. Well, I'm coming to the end here, and just to tire you, I've written a lot of conclusions here. First of all, the prediction of turbulent flow certainly will continue to be an important task for the aerodynamicist, and he will use the supercomputer as an invaluable tool in this. Computation of very high Reynolds numbers, aerodynamic flow fields, do still require the use of turbulence model. The high Reynolds number of engineering interests are not likely to ever be possible, but here, of course, I say this with some hesitation because I know right now some of my former students and colleagues are applying the massive parallel computers that are produced by thinking machines in the US to the turbulence problem. And of course, if you can speed up the computation by a factor of 1,000, it means that you can extend the Reynolds number range by a factor of 10 or so that it's not impossible that something will happening. But certainly, what we will see a lot of is direct simulation in combination with experiment and analysis, or is going to be essential for the understanding of the turbulence mechanism. We will always need careful laboratory experiments, and I suggest to some of you who are interested in wind tunnel and the like experiments to come up and look at the new wind tunnel that has recently been inaugurated at the Royal Institute for this kind of experiment. I also will plug a little bit for analysis, that it is a continuing useful tool, not only for trying to find approximate models, but also for understanding what you are doing with the computer and what you are doing in the laboratory. With that thoughts, I end my talk. Thank you very much.
Well, Professor Lander, thank you so much for your beautiful overview on the properties of turbulence. You have given us really very much insight in the capabilities of CFD, how it can be used as a powerful instrument to predict also the structure of turbulence. Well, if I'm allowed to cite one of the great men of hydrodynamics who have struggled to grasp what turbulence is, namely Horace Lamb, he once said, "In case I will succeed to come into heaven, I hope to get an enlightenment about two things, quantum electrodynamics and turbulence. Concerning my first wish, I feel very confident." Now, Horace Lamb would have been enlightened, at least partially, already on Earth if he would have got the chance to listen to your lecture, Professor Landal. Now, in memory of this lecture, I would like to give you a scroll, and I may read this scroll. The International Council of the Aeronautical Sciences is pleased to present the Daniel and Florence Guggenheim Award to Professor Martin Landal in recognition of his outstanding achievements in aeronautical sciences. At the 17th Congress, he presented the Daniel and Florence Guggenheim Memorial Lecture, CFD and Turbulence, September 1990, Stockholm, President Icas. Thank you. We close this session now. Well, that was one of the highlights of this Congress, but among those highlights there are another two which we have chosen to put at the beginning and at the end of this week. The first one was, as you know, the Guggenheim Memorial Lecture, having been presented by Professor Landal. He brilliantly gave us an outlook on the needs and capabilities of CFD to predict and to understand turbulent structures. Today, we now approach the other great event, and this is a presentation of the Icas von Karman Award for International Cooperation in Aeronautics. The Icas von Karman Award has been created in 1982. This was because the Council felt, according to the aims of Icas, the need of special appreciation of scientific achievements which have been elaborated within a joint international effort. International cooperation is in many cases the only way for many a country to contribute to the most advanced scientific, technological or engineering developments. The reasons can be referred to an order of magnitude of project costs which desire to be shared with other partners. They can also be better marketing possibilities for the project. Further on, there can be the need to use computational or experimental facilities of a quality or of a size not available in one single country, but there also can be the mere focusing of several dislocated intellectual capacities towards one goal to concentrate or to focus intellectual power. In 1982 in Seattle, it was the tri-national Tornado aircraft project which was awarded. Italy, the United Kingdom, Germany were the three parties. In 1984 in Toulouse, it was a French-German cooperation on the Airbus. In 1986 in London, it was a successful US, Italian, Japanese joint venture on the B757. In 1988 in Jerusalem, it was a 4-nation vortex flow experiment which was aimed to substantiate the Euler codes. The Netherlands, Germany, United States, Sweden were at that time the partners. The people who were awarded were 1982, Bernard Heath, Ricardo Mautino, and Gero Madelung. In 1984, Roger Betey, France, and Johann Scheffler, Germany. In 1986, Fausto Ceretti, Italy, Kenyo Uchino, Japan, and Everett Webb from the United States. And in 1988, last time in Jerusalem, George Struge, your Swedish countryman, Hans Hornung from Germany, Elsenar from the Netherlands, and Kai Tritsche from the USA got the award. This time, Icas has selected the CFMI engine in the General Electric SNECMA alliance. Relations between General Electric aircraft engines of the United States and SNECMA of France were initiated with the CF6 engine development for application to the Airbus A300 program. In the early 70s, a joint venture known as CFMI was launched to develop a 10-ton class high bypass ratio engine which had no specific application targeted at the time. The CFM56-2 engine, the first production model, was used to re-engine late model DC-8s for civil operators and KC-135 tanker airplanes for the US Air Force. A session featuring a smaller fan was initiated in 1982 for application to a stretched and modernized Boeing 737, the -300 series. The aircraft has proved exceedingly successful in the market, and CFM56-3 has achieved very high production rates for not only the B737-300, but also for the -400 and -500 derivatives as well. CFM56-2 and -3 versions have demonstrated very high reliability and low maintenance costs for airlines and military services around the world. Continued development has allowed the introduction of the CFM56-5 for the Airbus A320 and its derivatives. A high-thrust version, now approaching 15 tons output, is or has been certified for a very long range, -340. Thus, CFMI has a substantial family of modern engines for many applications and must be considered a major success by any standard. But the General Electric SNECMA alliance continues to develop. While development of the unducted fan has been slowed, the partnership evolved a new set of working relationships emphasizing component responsibilities for design, development, and manufacture. Interface definition and requirements are more complex than the core to low pressure system interface of the CFM series. This approach is being used for advanced versions of the CF6 engine as well. The relations are being formed for the prospective launch of a new, very large, very high bypass ratio civil engine. And this engine would be destined for large, long-range twins and must demonstrate the reliability needed for service. The two companies continue to explore opportunities for collaborative ventures in the large engine arena. Supersonic transport can create interesting opportunities for continuing the rather unique relations between the United States and the European companies in the aerospace field. Two gentlemen representing their companies and who will get the award. Those two gentlemen are here. It's Monsieur Gallois, President, Director General from SNECMA France, and Mr. Brian Rove, Senior Vice President, United States. I will now give them the award and they would like to come here to the microphone. I'm reading the document now. The International Council of the Aeronautical Sciences is pleased to present the Icas von Karman Medal to Louis Gallois, SNECMA France, and Brian Rowe, General Electric Aircraft Engines, United States of America, in recognition of the successful collaboration of the organizations in an important joint aeronautical achievement, which are at the 17th Congress, CFMI and General Electric SNECMA Alliance, September 1990, Stockholm, President Icas. Ladies and gentlemen, now I transfer the chair to Pete Peterson. He will be the chairman of the lecture. Thank you.
Thank you, Professor Loschka. It's a great honor for me to be here this afternoon to chair this lecture in concluding a very successful Congress and in honor of Theodore von Karman, who did so much to further international relationships in aeronautical sciences. He was, of course, one of the important founders of this society and a constant worker for international cooperation. I did go back and look into some of the background things that von Karman talked about, and I found an interesting reference in 1949, not too long after World War II, at a time when many European scientists and engineers were coming to the United States to work, and Professor von Karman felt that it was very important to build the research and the capabilities in other nations, and he said at that time, science progresses only if different schools of thought are encouraged. I believe we should provide our friends in Europe all aids to basic research. My present interest is in furthering international scientific cooperation. During his lifetime, Professor von Karman saw a great deal accomplished in the founding of AGARD and in the founding of Icas, but I'm sure he'd be even more pleased to see today the international group that has come together here and the strong work in the research in all the countries around the world. I want now to give you just a brief biographical sketch of each of the speakers. They are going to speak in series, but I will introduce both of them. Monsieur Louis Gallois was educated at the École de Haute Études Commerciales. He has graduate degrees in economic sciences and also at the École Nationale d'Administration. He was in the 70s, a public administrator of the Treasury Department, Ministry of Economy and Finance in France. Later in the 70s, financial attaché for Asia at the embassy in Japan. In 1978, head of the Aid to the Economic Development Bureau of the Treasury Department, Economic Affairs and Finance Ministry. Early in the 1980s, head of the Cabinet Office of the Research and Technology Ministry, and in 1982, General Director for Industry in the Industry Ministry. At that time also a member of the Atomic Energy Committee in France. 1986, Charge de Mission in the Ministry of Economy, Finance and Privatization, and from the Military Cabinet Office of the French Defense Ministry. And he is currently Chairman and Chief Executive Officer of SNECMA. Mr. Brian Rowe was born in London, England, and had his early education there. He received his BS in Mechanical Engineering with honors from King's College, Durham University, joined General Electric in the 50s, and spent his early years in design, development, and engineering. For 5 years, he was in the aircraft engine group at Lynn, Massachusetts, where he was the engineering manager for the CF700 J85 engines. He was named general manager of the CF6 project department in 1968 and elected vice president and general manager of the commercial engine projects division in 1972. In 1974, he became vice president and general manager of the airline programs division, and subsequently vice president and general manager of the aircraft engineering division in 1976. He was named to his present position in October 1979. He is the senior vice president and group executive of General Electric's aircraft engine business group with headquarters in Cincinnati, Ohio. He has the total responsibility for all aircraft engines, both military and commercial. Mr. Rowe is a fellow of the Royal Aeronautical Society and a member of the National Academy of Engineering in the United States. He was awarded the Legion d'Honneur by the French government in 1985. I believe the first speaker is Monsieur Gallois.
Mr. Chairman, ladies and gentlemen, first I have to ask you to excuse my poor English accent, but I think for a better understanding I have to speak in English. If we were to turn the clock back in your minds, 20 years to the early 70s, you would see an aviation industry that was moving across a new threshold. Aircraft noise problems were beginning to emerge as community awareness groups mounted pressure on airlines and airports. Jet fuel prices were beginning to take on the negative characteristics we were ourselves to encounter at the petrol pumps within a very few years. And there was a recognized need for a new technology engine to power new short to medium-range aircraft. Remember, high bypass technology had only been applied to the jumbo jets, but was not available for the short medium-range single-aisle aircraft at that time. Airbus industry was studying the joint European transport, known as the Jet 1 and Jet 2. These were intended from the beginning as successors to such airplanes as the BAC-111, DC-9, Tridents, Caravels, Mercures, and 727s. A new and highly efficient engine was required, with the support of its majority shareholder, the French government, SNECMA launched a competition to find a suitable partner in a joint venture to develop a new and modern 10-ton engine. That moment in time, almost 20 years ago, launched what was to become the forerunner for international cooperation between engine producers, the General Electric and SNECMA partnership, CFM International. In the brief time we have this afternoon, both Brian and myself would like to take you through this period and share some of the behind-the-scenes stories, the insights, and some lessons we have learned. At the time, in the early 70s, SNECMA had no real commercial market experience. Furthermore, having evaluated the resources needed, we realized that alone we couldn't undertake a program that we estimated could easily cost in excess of $1 billion to develop. So we needed a partner to help us proceed with the program. The agreement was to be structured in such a way as to make SNECMA an equal partner, taking part in design, development, manufacturing, marketing, and product support. We evaluated Pratt & Whitney, Rolls-Royce, and GE. In the end, we selected GE as our 50-50 partner to undertake the CFM56 program for several reasons. GE appeared the most interested in our project. It was as motivated as SNECMA to break into the 10-ton market with new technology, a market that was up until that time dominated by Pratt & Whitney. Technically, GE was already ahead of competition in hot section temperatures. The GE core engine was also going to benefit from US military support and experience. What helped our decision was that we already had a productive working relationship with GE that went back a couple of years. In 1969, SNECMA and GE had started working together on the CF6-50 program for the Airbus A300, as Mr. Chairman, you remind us. If you believe this all sounds too simple, you are right. Before we even began, the US administration let us know they were reluctant to let GE share the technology for the hot section, because the F101 engine core had a key military application. In the end, it took the presidents of both countries, Georges Pompidou from France and Richard Nixon from the United States, in Reykjavik, to get together and agree to let our two companies link up. That was only the first hurdle we faced and crossed. Then the second set of crises came out, because the expected market demand for a medium-range twin engine simply didn't materialize as planned. The Airbus project was halted, and we found ourselves sitting there with a large investment, a great engine, and no aircraft. Then the market changed. Fleet compliance, noise regulation, and higher fuel prices created the conditions, but it was in 78 or 79, when? 70? That caused United Airlines, Delta, and the cargo carrier Flying Tigers to decide to re-engine their DC-8s with the CFM56-2 engines. This first application for the CFM56 was for the DC-8 series known as the Super 70. The Super 70 is remarkably quiet and efficient, and it would probably be selling today if it was still in production. These first orders came in 79 and were followed in 80 with the United States Air Force's decision to re-engine the KC-135 tanker with CFM56 engines. For the first time in aviation history, an engine program was launched on re-engined aircraft. The CFM56 engines were quiet, clean-burning, fuel-efficient, and extremely reliable. We believe the key reason for this reliability was the extra severity of our early test efforts. And also we had time for developing it. We researched all previous commercial engine service problems and designed them out or tested to assure they would not be a problem for our customers. When we look at where we are today, over 7,000 engines sold firm and over 10,000 when options are included, application on 17 different aircraft for both military and commercial markets, a dispatch reliability record of 99.9%, the best of any engine in the air, an engine family comprised of 5 basic models from 18,000 to more than 30,000 pounds thrust that has a customer base of 137 airlines and military operators. A business model for international cooperation that has generated not just wealth for our nations, but also greater employment and has contributed to the expansion of lower-cost air travel. There is no doubt that we have come a long way in the past 20 years. While the initial startup and launching of the CFM family of engines appeared to be a tremendous challenge, the real story lies in how we have managed over these years to make the CFM engine program so successful. I know that in a moment, Brian Rowe will give you the reasons of the success of the SNECMA-GE cooperation. However, I would like to give my own views and draw a few philosophical conclusions from my very short personal trip through history. A French politician, lacking in neither wisdom nor humor, once said, with respect to a coalition which has been formed between two parties, union is a combat. I have kept that formula in my mind, and I think today that it applies rather well to the relation between SNECMA and GE. Face to face with the world leader in aero engine, it means GE, SNECMA had to demonstrate its capacities, affirm its ambition. I have to say that SNECMA's combat was above all a combat against itself, against its own habits, against the dirt it might shed on its own capacities. For GE, if I may speak on their behalf, the difficulties, although of another kind, were not less considerable. It was called to accept discussions with and sometimes objections from, and also to accept an equal partnership with a company far inferior in size to itself, whose reputation has not yet reached much further than the limits of what the French call the hexagon. And perhaps above all, a nationalized foreign company reputed as being very different, even if in reality the differences were less than was supposed, in terms of culture, attitude with regard to money, and links with government bodies. For all these reasons, the marriage between General Electric and SNECMA could have turned out to be simply a morganatic one. This has not been the case, thanks to the perceptiveness, the intelligence, the diplomacy, and the tact of the leaders of the two companies. Those who created and maintained the movement, let me to mention Gerhard Neumann, Jack Parker, Ed Wood, and Brian Rowe from GE. René Ravaud, Jean Solier, Jean-Claude Malroux, or Pierre Alési from SNECMA. However, there are other reasons why it has not been the case, less directly linked to the eminent role of this handful of great men. Firstly, as I have already said, because of the certainty shared by all those who took part that this project was a healthy one, which was going to succeed. Without this confidence, the CFM56 would not have withstood the desert crossing which separated the launch of the program from the first order for the engines. Secondly, thanks to the universality of technical language. This is what has enabled engineers from the two companies to understand each other, place mutual trust in each other, appreciate each other, and for many of them to form personal friendships. If there is one particular quality which our companies have in common, it is a very high level of their engineers and paradoxically their equally high level of modesty. As someone who does not come from an engineering background and is new in the business, this often strikes me as very surprising. But is not modesty the quality which contributes most to facilitating relations between people? Another factor behind our success has been the extreme simplicity of the cooperation formula adopted. Its creators were clever enough to realize that the most simple formula would be the most efficient and the one which would best withstand the test of time. With regard to the program, equality and plenitude in the responsibilities accorded to each partner. Complete liberty outside the program, but confidence, honesty, and loyalty in all aspects of our relation. I can add respect and friendship in a way where the Americans are more straightforward than the French. At the time of its conclusion, this alliance between SNECMA and GE, conceived with the aim of developing, manufacturing, and commercializing a new product with an equal share of tasks and responsibilities, was unprecedented. Over 20 years later, it remains a unique case within the industry. Naturally, it is unique in terms of longevity. In this respect, it will remain so not only because the CFM56 program will live on for at least another 30 years, but because we have just this very year signed another very important agreement on a new engine, the G90, and this new program has before it a life expectancy of half a century. This alliance is also unique in terms of its success, and last of all, through the freedom which it accords to each partner to live its life as it pleases. An extraordinary technical success, the CFM56 is also a fantastic human adventure. SNECMA is particularly honored to receive, together with GE, the Von Karman Award. I wish to thank in my name and on behalf of all SNECMA employees, the member of this Congress for the recognition. And now, Brian, it's my pleasure to pass the torch on to you.
Thank you very much, Louis. As Louis discussed, the primary target of the first CFM engines was a short to medium range twin, which in hindsight proved to be an excellent example of how the short-term fallacies of strategic planning. But also a reminder that if you have a good engine, it will find a home. because despite all the early projections, the joint European transport disappeared over the horizon and did not appear until 10 years later. While it wasn't launched in Europe as planned, it did happen in 1981 in the US with a derivative 737-300, and eventually in Europe with the launch of the Airbus A320. In fact, it took so long and involving that both applications required significant changes to the CFM56 basic design developed for the original aircraft. For example, when the Airbus was launched, an effort for the A320 in 1981, it became apparent that the existing Dash 2 engine, which we used on the re-engined DC-8, was not providing sufficient performance that the industry or Airbus so required. So just as we were getting our feet on the ground and our shipments were up to 200 per year, we had to go back and redesign the engine to get better SFC and a higher thrust. This was really an interesting time in the life of our project. We needed an engine with enough thrust and growth margin for the A320 and probable stretch versions that would follow. This engine, the 5A1, had an 11% fuel consumption improvement over the Dash 2. Such an SFC improvement obviously requires significant changes. Snecmer took on the design of a new fan that provided much higher efficiency well into the climb range, which is important for this short and medium range type aircraft. And most importantly, they developed a new efficient booster. Although not much difference may be seen in comparing the cross sections of the earlier and later versions, perhaps with the exception of the 5C, which is on the A340, the basic architecture of the CFM56 engine has been retained. However, as we at GE have done in the past, significant amount of technological improvements have been progressively infused into every component of the engine. Without going into the upgrading of the engines, apart from improving the fan efficiency, we've also improved the HP compressor, the pressure ratio, the HP and LP turbine efficiencies have been improved by over 4%, the pressure losses have been reduced throughout the engine, clearance control was significantly improved at all engine power levels during transients, and numerous new materials were introduced. And most importantly, the FADEC provided better overall performance and operability and obviously lower pilot workload. But in a sense, this operating of our engines is what really made the CFM56 so successful program in the long term. Building on its simple core with a single rotor, with a single stage HP turbine, the CFM56-2 evolved into a family of engines which started out at 22,000 pounds of thrust and now goes from 18,500 pounds to 34,000 pounds and could go even higher if the market developed. Over the past 20 years, continually improving performance has been one of our key objectives. We also had two other equal priorities. That was to deliver reliable engines and to provide first-class product support. I believe we've achieved both of those goals. I remember when the CFM56 program was initiated in 1971, the reliability target was to be as good as the JT8D. We've exceeded that target and since then have established new industry standards for reliability. And it's these outstanding levels of performance and reliability that have made the CFM56 engines the best-selling engines in the Western world for the last several years. Our customers know that reliability, maintainability, and maintenance costs are major operating factors which have strong influences on airplane economics. One obvious example is reducing engine shop visit rate, down from 0.2 to 0.15 per 1,000 hours. Now that may not seem like a lot, but that is the equivalent in operating costs of gaining 6 to 8% in fuel burn in today's fuel prices. These savings are also enhanced by the impact of not having to add extra spare engines. I would now like to share with you what I see ahead for the CFM program and also give you some of my personal insight into international agreements, at least what I believe makes them work. As for the future of our engine family beyond 34,000 pounds, which will be available in 1994, we're looking at several growth opportunities. Initially, we're looking at thrust levels up to 36,000 pounds, which will require increased airflow and some increases in temperature and new materials. Using the current CFM56 core with 2 counter-rotating fans, it will be possible to reach 40,000 pounds of thrust level with an SFC reduction of 6 to 10%. Other preliminary studies are also being looked into, including changing the cycle of the engine by significantly increasing the current 6.7 bypass ratio to 10 or 15. We are also seriously studying a new core, which could be scaled down from the GE90 design. Our objectives here is to improve our fuel consumption by over 7% over any present engine in that particular thrust class. Also, we are looking at the very important parameters of reducing noise and emission characteristics of the engine to ensure competitive advantage way into the next century. I might add that our present CFM56 meets with large margin both current noise and pollution regulations, but as you all know, we have to be ready to do even better. You may ask, why has SNECMA and GE relationship been so successful? The one lesson you can draw from the CFMI example in international cooperation is that Louis and I have talked about today. It is a program such as CFM and the companies that back it must be particularly robust to survive the changes in external factors that exert a major influence in success and failure. In fact, when we started the program, there was a period there which was missed by 1 day because we got the order of cancelling the engine or going ahead on the re-engine DC-8. And I can say we were very lucky that we didn't cancel the engine that day because we got the order the next day from Delta and United. And that was a big day from all of us, as you can imagine. But most importantly, both companies had the staying power. In looking back, we were fortunate to have 2 leaders at the start of the program, as Louis mentioned, René Revaux of SNECMA and Gerhard Neumann of GE, who wanted it to work and didn't let ideological differences get in the way. Also, both companies transferred people and their families to each other's plants to reduce the cultural barriers. Many of these people are now in key positions and not only have a good working relationship, but are also personal friends. We continue this interchange of people and ideas throughout regular business and social meetings and have a great respect for each other's technical capabilities. However, like everything in life, it takes a lot of effort to make any relationship work. And the management of the partnership must be particularly alert to constantly test their assumptions against external circumstances. They must be ready to modify a program to reflect the fundamental market and economic changes. And I might add, we've had tremendous relationship in this regard with SNECMA, and they've been equally responsive with us in changing direction very rapidly. Also, you must have steady nerves and guts, if you will stick out the short-term fluctuations. You must be prepared to discuss problems openly, and most important, have no hidden agendas. What is needed is the ability to distinguish between fundamental change and short-term fluctuations. And of course, most importantly, have a lot of good luck. However, as the saying goes, the harder you work, the luckier you get. No question, GE and SNECMA started with a great engine, but we're also fortunate to have the right engine at the right time as the market changed. That's why our orders since the first engine was shipped to Douglas re-engineering facility in Tulsa in 1981 have grown to over $30 billion, and we expect to sell even more. In addition, since many CFM56 core components are common with those other GE programs, like the F-110 for the B-1 and the B-2, the F-101 for the B-1 and the B-2, the F-110 for the F-14 and 16 fighters, we were able to create significant economies which are a benefit to our customers, both military and commercial, as well as to our program partners. Other good things have happened as a result of this partnership. SNECMA has demonstrated to the industry that its design and development capabilities are world-class, and they are playing a full role in marketing and product support of the engine throughout the world. Also, both our shareholders and our governments are pleased. The French government is satisfied that this cooperation has led to large industrial exports from France to the world markets. And the US government, which initially had great concerns about technology transfer, is now satisfied that Snecma and GE have adequately safeguarded this technology while benefiting the economic strength of both countries. Clearly today, the US government is in favor of such international cooperative programs. The success of the CFM56 program has also resulted in a strong mutual supportive working relationship between GE and Snecma for future programs. One example is the unducted fan. While not in the market yet, it is a viable standby technology in case we have a large increase in fuel prices, which is becoming a lot more relevant today. As we look down the road, there is no doubt that aviation will need an engine with higher thrust, improved fuel economy, and proven reliability. An engine that can give us up to 95,000 pounds of thrust and a fuel efficiency up to 10% greater than anything flying today. And we call that engine the G90. That's the one that GE, Snecma, and our other partners are working on. This engine will have as its core the proven technology of work that we did with NASA on the energy efficient engine, and will incorporate all the lessons learned from our GE and CFM56 families. The gas generator has a higher pressure ratio and fewer stages than any of today's high bypass engines. And its proven technology is state-of-the-art, a tough combination to beat. We'll also have a low emissions combustor, and our experience with the unducted fan will contribute to the composite technology that is being used in our low-speed, ultra-quiet fan. If there's one message that out of both of our talks today, I hope it is that we communicated a better understanding that no one nation can dominate world aerospace market, and the best products will require global brains to help develop them. This takes an expression we use at GE, share to gain, to its ultimate. By working together, everyone gains. Relationships must last through economic cycles, political headwinds, and through temptations of competing opportunities. The break-even time on these products make company chairmen and shareholders very uncomfortable. And this is why it's very important to work on products that are truly superior. As you can imagine, this is no business for the faint of heart. Sometimes all the business numbers just don't make sense. You're not in control of the market, but you are in control of giving your customers the best quality products and service possible, which is, I feel, have been one of the keys to the CFM success. In our business, bringing an engine from development phase to production and into service is very, very lengthy. The cycle is long, and the cost of losing comparative technology advantage is great. That partners must take that commitment is a long-term cooperation. And as you heard today, international cooperative programs are not easy, and many times are full of surprises. But there is no alternative in our industry if we want to reach the technology goals that we have set for our future. On behalf of GE and Snecma employees, I wish to thank you, the members of the 17th Congress, for this most prestigious von Karman Award, and thank you for having GE Aircraft Engines and Snecma on your program today. Thank you all very much.
Is this my, yes, it's on. We do have some time for questions. If there are any. Okay, I believe not. I think that was certainly a very excellent lecture from both Monsieur Galois and Mr. Rowe. We certainly appreciate that. And I would like then to turn the meeting over to Professor Lashka for the closing ceremonies.
Yes. Well, ladies and gentlemen, we are immediately proceeding to the closing session, so we would have another 10 minutes time for it. The time has come to say farewell to each other, at least for those who missed to attend the dinner in the Opera Kelleran tonight. At the Opera in Kelleran, we still will have two highlights. One will be the presentation of the Icas Maurice Roy Award, and it will be Joseph Singer who will get it. The other event will be the presentation of the Icas McCarthy Award. This award will be given to that student who achieved the best performance at the student session during this Icas Congress. 24 students from many countries, I haven't counted them, but from more than 10 countries have presented those papers, and the committee has chosen the best one. And the students who will get the award is John Crépeau, he has a French name, I would say Crépeau, University of Utah, USA. It will be tonight. Now, ladies and gentlemen, I feel Icas, by the present Congress, has again contributed in a substantial way to the exchange of science and technology in the aeronautical field, exchange between more than 30 countries in the world for more than 550 people. The Swedish Aerospace Society has shown up an outstanding performance in preparing this Congress. I therefore would like to express my very thank to its president, Mr. Lars Andersen, and also to the president of the organizing committee, Mr. Göran Lilja, and to their team for having done this so perfectly. Thank you so much, and I would like to give them an applause. Well, I said this in the context of all attendees here, as I hope. But I say this also in the context of our next Congress, for which the present one served really as a good promotion. Let me now give you some information about Icas in the future. Several important decisions have been made by the Council, and I have noted some of them which I believe you ought to know. First, it is a principle of Icas as an international organization to move the Secretariat after some years to another hosting society which can give us the necessary support. As you know, in the past years, the Secretariat had its home base at the Royal Aeronautical Society. And the Royal Aeronautical Society gave Icas any help needed, and we are very grateful for it. It was a great experience to work together with the Royal Aeronautical Society. Besides the society, I especially would like to thank the two ladies, Miss Maria Aprilante and Mrs. Sue Arkell, who have run the Secretariat actively, who have run it so efficiently, with patience, and, as I believe, also with great charm. The Royal Society took a heavy burden on its shoulder. It was therefore felt that after 2 cycles of very successful operation, the Secretariat should be shifted to another country. And this country will be the Netherlands right after the Congress. That means the new address of the Secretariat will be the Dutch Aerospace Society at the Netherlands Aerospace Establishment, NLR, in Amsterdam. Because of the shift, a new executive secretary had to be nominated. He has to belong to the hosting country. Professor Alec Young will therefore terminate his duties. He himself did a marvelous job, and by his own high scientific reputation, he himself was an outstanding promotion for Icas. I think we should also give him a applause. Well, as a new executive secretary, Fred Stark from the Dutch Aerospace Society has been elected. And if I am right, he is right to the corner and he will show you his place. Thanks to him and thanks also to your society for taking over the duties associated with the Secretariat. Further on, I would like to tell you that the present Program Committee Chairman, Pete Peterson, will remain in office. He has done also such a beautiful work that everybody thought we can't find a better one. The same is the case with the honorary treasurer, who is also an officer. John Swihart has improved the finance situation of Icas appreciably, so he has been chosen again as honorary treasurer. According to the Constitution, also a new president has been elected. And this new president is Professor Paolo Santini, president of the Italian Aerospace Society, full professor at the university in Rome. He is sitting aside. Further on, I would like to inform you on the next Congress venue. There was already a rumor, as you know, that an invitation of the Chinese society was existent. And this invitation has been accepted by the Council. That means that the next Congress will be in Beijing. Our Chinese friends have offered really attractive conditions, special fares, I can tell you around $700 for the two-way trip to Beijing from Europe or from the United States. They will also offer 4-category rooms, start between $40 and $150, and a low registration fee. It is also my deep desire, it is also my deep desire, I think it's now the right place to say my thanks to the authors and to thank all the chairmen for the work. And I also would like to thank all the participants, all the commentators, all those who have participated in the discussion. Well, ladies and gentlemen, I only can say, see you all again in Beijing in 2 years from now. And now, ladies and gentlemen, I would like to hand over to the presidency to Paolo Santini.
Thank you, Boris. Thank you for all you have said and all you have done during these 4 years of your presidency. Taking over Icas is a very prestigious thing, but it's also a very hard job for several reasons. First of all, because Icas in itself is a great thing. Second, because the last 4 to 8 years have seen a continuous improvement of Icas. We have enlarged our responsibilities, we enlarged, and we have many now, more than 30 countries belonging to Icas. Recently, just yesterday, Boris probably forgot to say it, we had two new members, South Korea and Pakistan. That means that also the influence of Icas is extending also towards the Southeast Asia. We held the next meeting in Beijing. And all these things, as you understand, are such that the responsibility of not only of the president, but also of all the committees of the Icas will be difficult in the next 2 years. But we are fortunate that we have very good co-workers, starting from the people that has been mentioned by Boris, the Technical Program Committee, the Executive Committee, the Finance Committee. And you see, there are people, many of these people, we start working for the next Congress after this weekend. 2 years from now, seems many, but it's not so, because you need to start immediately to have just 2 years of work for what, you will say? For 5 years Congress seems to be. You burn everything, your 2 years work in 5 days. Yes, that's true. But what is important, not the 5 days, are the 2 years, where everybody works and everybody prepares. And this is the progress of the human science in general, and particularly of Icas. The 2 books, very heavy, I don't know how many of us will be able to bring it upon the airplane, but those 2 big books that we receive every 2 years are the result, are the abstract of the progress made by the aeronautical science and technology during these 2 years. I think the most important things that happen in the aeronautics are contained in those 2 heavy books. That's why I see already Monday morning, I think Pete Peterson will start thinking of his program committee in 1 year from now to select the papers and sending around letters for the call of papers, and the executive committee secretary preparing other letters for other things, and all this. The only one we probably will not start immediately work is the president. It will take maybe some more days for rest. So as I would like to join my friend Boris in welcoming you here tonight and welcoming you since now, 2 years from now in Beijing. Thank you for everything.
Well, Paolo, I wish you all success for your presidency to the benefit of Icas.
Thank you.
And I close the Congress.
Again.